Okay, AP Calculus, we're going to get rolling into the last real section that we're going to cover here in Chapter 1. And again, not really related to anything else, but just another section that we thought we would revisit from the last couple of years, this one being on exponential and logarithmic functions, which are one of the major classes of functions that we're going to be dealing with here throughout the course of the year once we start talking about derivatives and integrals and things of that nature when we actually dive into our calculus content. So exponential and log functions, two different types, but they're certainly related to one another. So, and it's usually one that people tend to remember pretty well from the last couple of years. When we talk about a function exhibiting what we call exponential growth, the main important distinction to draw here between an exponential function and a linear function has to do with their rate of increase or decrease. And in a linear function, as I think you guys know, we can expect to see, don't bother writing this down, we can expect to see a constant rate of change no matter where it is that we measure it here. So if you notice, I'm just plotting a series of points, and each time I'm rising 2 and I'm running 3, and that's what we have right there for a linear function. The rate of growth is always going to be the same, and of course we call the rate of change of a function its slope. So the hallmark of a linear function is one whose slope is constant no matter where we measure it. But exponential functions, of course, do something different. Now, in the simplest way of describing it, exponential functions, when we talk about exponential growth, I should say, are functions that grow at a growing rate, although it's actually a little bit more complicated than just that. So here's the generic format for an exponential function. F of x is equal to a multiplied by c to the x power. Now, two important things to note right there, that the variable of this function, as defined way that we named it, f of x, means that x is the only variable in this function. And a and c are what we call arbitrary constants. They're going to change from problem to problem, but within the course of each individual problem, a and c remain constant. And if you're wondering who to credit for this wonderful system of notation right here, it's actually the French mathematician and philosopher René Descartes, who we're going to talk about in here a lot, who introduced this convention of using of using letters at the end of the alphabet, such as x, y, and z, to represent your variables, your unknowns, and using the letters at the beginning of the alphabet, most commonly a, b, and c, to represent your constants. And as I'm looking at this, one of the first things I thought for a moment, and you may have too, is okay, we used a for the first constant, why did we use c for the second and not b? Well, there's certainly no great reason for it. You could have used b as well, but we do often like to use the constants c, for obvious reasons, to remind you guys that that particular number is going to remain constant within each problem. And k is another one that we use a lot when c has already been used. So the important thing about an exponential function is that the variable is located in the exponent. Let's draw a distinction between that and maybe a function that would look something like this. G of x is equal to x squared. Now, some people are going to incorrectly say that g of x is an exponential function because it contains an exponent. But just to make sure that we understand the difference between the two here, everybody, in an exponential function such as f of x, it's the variable that's located in the exponent. And in this function here, g of x, which of course is just a simple polynomial or a quadratic, the variable is the base of that exponent, and the exponent remains constant. So most of us seem to know that pretty well. So if we're trying to get a handle on what an exponential function looks like, the simplest exponential function we can draw would simply be f of x is equal to 2 to the x power. Now, if that surprises you just a little bit that using 2 is the simplest number that's out there, I'll just remind you that if we drew the function f of x equals 1 to the x, it would be a pretty boring function because 1 to any power is equal to 1. So that really wouldn't look like an exponential function at all, although I suppose technically it would be. That would really just look like a constant function. And the same thing would happen with 0 to the x power. But it's not until you let your base be something other than 1 or 0 that interesting things actually start to happen. And 2 is the simplest way to see that. So Just for fun, even though I know we know this information pretty well here already, I'm going to go ahead and make a quick table of values here, all right, just to refresh your memory on what actually happens with an exponential function. And I know that sideways tables here are not everybody's cup of tea, but we use them a decent amount throughout the course of this year. So if I were to just go nice and simple with my x values and have them start at 0 and increase by 1 each step along the way, let's see what we can do with this. So we're taking 2 to each of these powers. Well, 2 to the 0 power is 1, 2 to the first is 2, 2 squared is 4, we're going to get an 8, a 16, and a 32. Now we're obviously not going to plot all of these points because 532 is going to be a little bit off my graph. But what we should notice is that as our x values increase at a constant rate, as we're adding 1 each time, that's kind of our delta x, our delta y is no longer constant the way that it would have been in a linear function. We increase by 1, then we increase by 2, then by 4, then by 8, then by 16, and you'll notice then that we're basically just doubling the amount each time. But if you look at it in terms of addition, this is kind of interesting. Whatever your previous number, your previous y value was, that's what you're going to increase now by the next time. So the phrase that we're going to use a lot this year is that this type of exponential function increases, but at an increasing rate. And these red numbers down here represent the amount of increase. And the further we go to the right, the more those numbers increase. So the function increases at an increasing rate. Plotting these points, as many as we can anyway, we've got the point 0, 1, 1, 2, we've got 2, 8, and beyond that it's probably too much for the graph here, but that does kind of give us a sense that this thing is going to look a lot like this. And when we draw just half of that graph right there, a lot of Algebra 2 students, when they see this function for the first time, or even Algebra 1 for that matter, start to think that what they're dealing with here is a parabola. They say, okay, that looks like the right half, and I'm going to go ahead now and just draw the left half to do the exact same thing, and so this is actually a quadratic or a parabolic function. Well, if we thought that, everybody, we're only looking at about half the story. So what I'm going to do now is make another quick table here, same function right here, f and then f of x. And now what we're going to play with is what happens when we start putting in negative integers. If we think about domain and range, everybody, for this function, let's have that conversation about domain. The question is, what values can you put in for x and get a real result? So the question you should be asking now is, I can take 2 to what kind of power and get it to work out? Positive numbers? Clearly, that worked. Negative numbers? That's what we're about to get into now. The answer to that is yes also. 0? Yeah, that worked out as well. So actually, guys, the domain of this exponential function is going to be all real numbers. There's no number that you cannot raise 2 to that power and get a real result. So let's start putting in some negative numbers, and again, we're not going to plot all of these most likely, but I think I'll just go to -4, and let's see what happens there. And remember, everybody, that when we try to take 2 to the negative first power, let's do this down here, we rewrite that as 1 over 2 to the first power, which of course just becomes a 1/2. So 2 to the negative first power is going to give us 1/2. And the same trick applies with any other negative exponent. 2 to the negative second becomes 1 over 2 squared, and that's going to get us 1/4. The negative third power will give us a 1/8. The negative fourth power will give us a 1/16. And what you might start to notice here, if you didn't know this already, is if we take a look at the y values in our table that start right here and then kind of finish up down here, they all certainly have one thing in common. They're all positive. So think about that for just a second. If we go back to this function right here, does it seem possible to you guys to take a positive base like 2 to a particular power and end up with 0 for your result? The answer to that is no, it's not possible. The only way to get 0 as a result to an exponent expression is if you started with 0 as the base. So you're never going to get 0 as a y value in the range of this function. Furthermore, it certainly looks right now, since all of my y values are positive, that it would be impossible to get a negative y value coming out of this function. That's also correct. You cannot take a positive base such as 2 to any power and get a negative result to come out of it. And as we start plotting these from right to left, we're at -1, 1/2, so right about there, -2 and 1/4, -3 and 1/8, and moving from right to left, what we start to see is that these points are dropping lower and lower each time, and they're getting closer to the x-axis. But because we said that it's impossible to get 0 for a y value, what we have here, everybody, I know you know the phrase well, is a horizontal asymptote right here at the x-axis. And this particular horizontal asymptote works well with and matches the definition that I think you guys already have for horizontal asymptote, a line that your function approaches but never touches and never crosses. Now let me clarify, we are going to change that definition when we get into chapter 2, but for our purposes right now with exponential functions, it seems to work pretty well. So I think you guys know this. We actually end up drawing the function more or less parallel to that x-axis and the asymptote, even though we know that it's not. That's really kind of the impressionistic graph that we make for it. So, all right, everybody, so this is what we have. We talked about the domain of the function, and now that we've graphed things in a little bit more detail, I think it's okay to talk about the range of the function now. And as we look at it, it certainly appears that every single y value that we've gotten, or we're ever going to get out of this function, need to be up above the x-axis. So for your range, we would simply say that y needs to be greater than 0. So always a good discussion to have there with domain and range of a function. All right, guys, that's probably something that you remembered pretty well over the years here, but let's keep going and let's talk about a couple of variations on that function. So if we made our exponent negative, everybody, f of x is equal to 2 to the negative x, let's start talking about what that one would look like. All right, so again, probably the best way to do this, if you're not 100% certain about what change happens to your parent graph when your x becomes negative, we can always do a quick table of values. And I do believe that at this level, and with your level of intelligence, everybody, we can do this mentally rather than having to write it out. I do just want to take a second and draw the generic parent graph here as like a dotted green. Oops, that looked something like that. So what happens now when our exponent becomes negative? So when we go to stick a 0 into this function, well, the negative still becomes 0 there, and 2 to the 0 is still 1. So we're going to hit that same point right there at 0, 1. What happens, let's say, when x is 2? When we evaluate f of 2, this function becomes 2 to the negative second power, which is going to give us 1/4. So 2 to the right and 1/4 of a unit up above. Okay, interesting and different from what we normally saw in our parent function. So now the question might be interesting. What happens if we chose a negative value for x? So if I evaluated f of -2, in fact this one I am going to write out, f of -2, that becomes 2, and the exponent will be the opposite of -2, which now becomes +2, which just gives us 4. So we have the point -2, 4, and I really think, everybody, that once you've drawn 3 points there, you understand what's happening in this graph. We know that exponential functions, more or less, mostly all take on the exact same shape. It's just a question of what direction it opens. So in case you've forgotten, the significance then, everybody, of changing the sign on your, actually all your x's, is that it reflects your parent graph over the y-axis looking something like this. So the normal green graph just rotated 180 degrees around that y-axis, and we got this new graph right here. So hopefully that's something you remember from previous years. All right, let's make another shift now, everybody. What does it do to our parent graph, or really, what does it do to any function, if we now put a negative directly in front of the entire thing? So again, there's the parent graph in green, y equals 2 to the x. Now we want to take the opposite of 2 to the x. So let's play around with that a little bit, although this one is one I would expect you guys to remember maybe even a little bit better than the previous one that we did. So go ahead and put in a 0. And remember, everybody, that when the function is written as this without parentheses, we don't read this as -2 to the x power. What we read it as, and this is important, is the opposite of 2 to the x. And without parentheses, you've got to revert to something you did in 7th grade, everybody, and that would be PEMDAS, order of operations. Please excuse my dear Aunt Sally. And if we recall, exponents right here take precedence over what we really have with that negative, which is multiplication. This function really could be rewritten as -1 multiplied by 2 to the x power. And exponents have to come first. So when I give you a value for x, we're going to evaluate +2 raised to that power, and then we're going to multiply that result by -1. So when we put in a 0, 2 to the 0 power is 1, and the opposite of 1 is going to get us -1. So we start with that point there. And some of you, I think, already know what this graph is going to look like, but it certainly doesn't hurt us to do 1 or 2 more. When I put in a 2, 2 squared right here becomes 4, and the opposite of that is going to be -4. And when I put in a -2, 2 to the -2 is 1/4, and the opposite of that is -1/4, and we're looking right there. So I think at that point, everybody, we see what we need to see, that this graph is going to look something like that. So unlike the graph that we did in the first example, when we put a negative out in front of the entire function, that then is going to rotate our original parent graph around the x-axis. It's going to reflect it vertically. And the last one that I wanted to do with you guys on this slide before we move on, let's do both of the things that we just discussed. We would read this as f of x equals the opposite of 2 to the -x. So if we think about the parent graph here, everybody, which of course hasn't changed and still looks like this one right over here, let's think about what changes we can expect to see here. The negative on the x directly should give us a, what do I want to call it, a vertical axis of symmetry here where we would flip it over the y-axis, okay? But the negative out in front of the whole thing should have us flip over the horizontal line, the x-axis, so this really should do both. But just to make sure we've got it right, let's go ahead and play. And this one I am going to write out here. So let's just go with a quick x and then f of x table here and see where we're at. And I'm going to pick 0 and 2 and -2, same x values we've been choosing lately. So when we plug in a 0, 2 to the -0 power is still 2 to the 0, and it's still 1, and the opposite of that is going to be -1. Plugging in a +2, this now becomes 2 to the -2nd power, which is 1/4, and the opposite of that is -1/4. And lastly, when we put in -2, this now becomes 2 to the +2nd power, which is 4, and the opposite of that is going to be -4. So let's plot those 3 points, 0, -1. We have 2, -1/4, and we have -2, -4. And what are we seeing here? This one looks like this graph has been flipped in both ways compared to the parent graph. Looks like it's been reflected both over the x-axis and also over the y-axis as well. Okay, everybody, so that's just kind of a quick recap of what exponential functions look like. And the one thing I did want to point out very quickly, I think you guys know this, but just in case we've forgotten, is that when we go and we graph exponential functions with different bases, the difference that that base makes is actually pretty minor and pretty negligible. So let's go ahead and graph 2 to the x power on our calculator, which of course is what we were just working with right here. So the next question that might be logical is, what if the base increased and instead we took it as 3 to the x power? Well, if we think about it for just a second, if you put in 0 to either one of these functions, they're both going to give you the same y value of 1. But if you put in positive numbers, 3 to the 1st power is going to be greater than 2 to the 1st power. Likewise, 3 to the 2nd power is going to be greater than 2 to the 2nd power. So on the right half of these graphs here, this function that we're dealing with now, 3 to the x, should exceed or be higher than the blue curve that we had already. But when you go in the other direction, to the left of the origin, when you let x become a negative number, let's think about that. 2 to the -1st power we said was -1/2. 3 to the -1st power, +1/2, 3 to the -1st power is going to be 1/3, which is actually less than 1/2. So when we graph this, everybody, I'm hoping you kind of visualize that already. When we graph it, we can see that they pass through the same point, which is 0, 1. And to the right of that point, 3 to the x is higher than the graph of 2 to the x. But as we move to the left, and I'm going to zoom in on this just a little bit so you guys can see it maybe a little bit better, and I'm just going to go zoom in and hit a couple of points here. We can see that on the left-hand side, 3 to the x is actually less than, it's actually below 2 to the x. Let me hit escape to get out of here. Let me hit tab, and we got to hit tab again. Nope. I still have to hit escape here. Okay, gotcha. So that'll put us there. All right, and when I hit tab, let's just see what happens, guys, if we were to hit something like 5 to the x power. Well, as you'd probably expect, on the right, this thing should increase even faster than 3 to the x, and on the left, it should come even lower. The one other thing that I think is kind of interesting, let me take it back to a standard zoom, everybody. So I'm going to hit menu, number 4, and go back to number 5 right here for hitting a standard zoom. The one that I find kind of interesting is what if we went with something like 1.2? Let's go with that, raised to the x power. We talked quite a few minutes ago about how 1 to the x isn't really an exponential function because it just ends up with a constant value each time. But as the base of that exponential function gets closer to 1, we can start to see that this function doesn't have as much curve to it, and it's only increasing at a much slower rate there. And honestly, a lot of the exponential growth that you might see out there in the world, something like the number of cases of a virus, for example, or economic growth or population growth, it's very rare that things tend to double in every iteration right there. So even the blue, the red, and the black graph, you don't see that a ton out there in the world. However, that purple graph of slow exponential growth is one you're likely to see a little bit more often. Okay. So that's all I wanted to say about exponential functions. I think as you guys dive in there, you'll remember what's going on there pretty well. But let's talk about logarithmic functions, everybody. And logarithms are kind of the tit to the tat right here, the yin to the yang with exponential functions. If you understand exponential functions, which most people do, then coming up with an understanding of a logarithmic function is a small leap from that, although it is more difficult. And most people internalize exponential functions pretty well between Algebra 2 and pre-calc, but logarithmic functions can be harder. So our generic definition of a logarithmic function is one that would be written like this, where f of x is equal to some arbitrary constant a multiplied by a logarithm of a base that we're calling b, and then the x comes at the end of that. Now, that's all well and good, but writing that down and saying the letters and putting a box around it doesn't really help if we have forgotten what a logarithm is. So let's just take a moment and let's try to remember two things about logarithms. First of all, when they ask you to evaluate a logarithmic expression, we need to remember exactly what that means. So log base 2 of 32 is asking this question. 2, we're using our base right here, 2 raised to what power, in fact I'm going to write this over here, that 2 raised to what power is equal to 32. Logarithms are just another way of expressing exponents, but the difference here, the question that they're asking you is, what is the power that will make this happen? Well, as I focus on what's over here in black, hopefully we remember this and we saw it just a minute ago, it's 2 to the 5th power that's going to get you 32. Which I can always remember because 3 plus 2 is equal to 5. I have a lot of really stupid ways of remembering things, guys, but I've been doing that in my head since probably about Algebra 1. Anyway, so with that in mind, if we go back to the original logarithmic expression here, the answer to that, log base 2 of 32, is going to equal 5. So the same information, and this was my weird attempt at typing a double arrow here, guys, and it didn't work very well, but anyway, the same information is expressed in both the left and the right half of this statement. It is true that log base 2 of 32 is equal to 5 for the same reason that it's true that 2 to the 5th is equal to 32. Now, quick little vocab lesson. This little number that is subscripted after the log is called the base of your logarithm. You probably remember that because when we read this expression, we instinctively say log base 2. but I want to remind you guys of something cool that sometimes gets lost in translation. If I slide over here to the right and I look at the equation 2 to the 5th is equal to 32, that same number, 2, is once again called the base. It's just that on the right, it's the base of an exponent. On the left, it's the base of a logarithm. But it's not a coincidence that they're called the same thing. All right, what else do we have right here? If we focused on the expression over here on the right, that 5 then is called your exponent or your power. As we move over here to the left now, log base 2 of 32, that 5 is still going to be called the exact same thing, everybody. What we are looking for when we are asked to evaluate a logarithm is we're looking for an exponent or a power. The question here was, as we looked at right here, the question is 2 to what power is equal to 32? So the answer to a logarithm is your exponent. And then everybody struggles on what to call this number right here. Okay, what is that 32? Well, the answer to that question really comes from the fact, and I hope you guys have seen it, that on the left and the right-hand side, the vocab is exactly the same. So let me ask you now, what do you call the 32 over here? You were asked to take a base, 2, to an exponent, 5. And remember, everybody, that an exponent is just a more efficient way of expressing the simple operation of multiplication. We were being asked, what's the answer to that multiplication problem? And the answer to that is a product. This is a word that you probably learned back in 4th grade. The answer to a multiplication problem is called the product. So over here on the right, that 32 is once again called the product in your logarithm. So that's just kind of a refresher here on what a logarithm actually is. And now that we've talked about that a little bit more, let's go ahead and discuss once more what a logarithmic function is asking us to do. And that's probably best illustrated by, again, doing a more basic example here. What happens if we take the simplest logarithmic function we can come up with? F of x is equal to log base 2 of x. So we're going to begin, yet again, by making a table here with x values and then figuring out f of x values that go along with them. So let's get started here. Now you guys noticed that when I did the exponential function a while ago, the first thing I did was I started with 0. So let's go ahead and think about what happens when we evaluate f of 0 in this function, and I think we might want to write this out. It's log base 2 of 0. And I hate to be rudimentary about this, but most of us at this level, especially at the beginning of the year, still need to translate this into an exponential way of thinking. The question right now is 2 raised to what power is going to equal 0? I'll let you think about that for a second, although we already talked about it today. The answer is there is no answer. You cannot take a positive base like 2 to any power and get it to equal 0 as a result. So what that tells us, everybody, is there is no value here for f of 0, and that tells you something important. 0 is not in the domain of this function. There is no real result that we can get out of this function by putting x into it. So that was worth talking about, but I didn't want to just say or assume here that you guys knew that. So that's the reason why. So with that in mind, let's move along. Let's put in a 1 right there. So f of 1 is going to be the log base 2 of 1. And the question now is 2 raised to what power is equal to 1? And the answer to that, 0. How about when we put in a 2? So now we're saying f of 2 is log base 2 of 2. Sorry, that's ugly. So the question, 2 to what power is equal to 2? And that's going to get us a 1. Now, it certainly looks like we have a nice simple pattern going in our table, and it looks like 3 would be the next number that we would want to put in. But if we were to try to evaluate f of 3, listen to the question that we're now asking. 2 raised to what power is equal to 3? Well, there certainly is an answer to that question. There is a power you can raise 2 to get 3, but it's going to be an irrational answer, everybody. It's going to be an ugly decimal if we try to express it that way. So while there is a value here that works, and 3 is in the domain of this function, it's an ugly one to come up with. It's not one that we could do without a calculator, so we're going to skip the 3 right now. And we're going to try to be intelligent and selective here about the next x value that we can choose. And if you're thinking down the line, I think you guys realize that 4 is going to work out just fine. So when we go to take f of 4, which is log base 2 of 4, the question now becomes 2 raised to what power is equal to 4? And the answer to that is 2. Humor me with one more. The next smart x value to put in here, you guys, would be 8. And now, log base 2 of 8 means 2 to what power equals 8, and the answer there is 3. Now, we could keep going, but I think you guys can see right now what it is that we need to see. Normally, when we did a table, did I keep it here for the exponential functions? Yeah, when we looked at this table right over here, you guys noticed that our x values here, 0, 1, 2, 3, 4, and 5, they followed a nice simple pattern of increasing by 1. And it was the range, the y values, that increased at an increasing rate. They changed each time. Now, as we look at this logarithmic function, now, you guys, it was actually, I didn't intend it to be this way, but it was actually the y values that ended up following a nice simple pattern of increase, and it's the x values that increase, let's see, by 1, by 2, by 1, by 1, by 2, and by 4 right there. It's the x values that are following a slightly different pattern. So let's see what happens when we try to graph this. You cannot get a point right here when you put in 0, but we do get the ordered pair 1, 0. We got the ordered pair 2, 1. We have 4, 2 right there, and we have 8 and 3. Okay, and at this point, everybody, this is what the graph looks like, and this is a curve that we would say is increasing at a decreasing rate. Now, it just kind of stops unnaturally there at the point 1, 0, so it might be worth thinking about, are there other values of x that we might be able to consider that we haven't gotten to just yet? So if we were to continue going with this, let's have our discussion go on just a little more. We know that it doesn't work to put 0 into this function. What about a negative number? Can we evaluate the log base 2 of negative 1? Well, again, translating that question, it becomes 2 raised to what power is equal to negative 1? Once again, there is no solution to that question right there. You cannot take 2 to a power and get a negative result. So we can't put 0 in, we can't put negative numbers in, but there is one type of number we haven't talked about yet, and that would be fractional numbers, everybody. What happens if we put in 1/2? Log base 2 of 1/2 means 2 to what power is equal to 1/2? And the answer to that is going to be negative 1. What if we were smart now and put in a 1/4? 2 to what power is equal to a 1/4? Answer to that, negative 2. And let's go ahead and put in a 1/8, which is going to get us a negative 3. And we could go further on that line, but I think we get what's going on. So when we try to plot these, 1/2, negative 1, okay, 1/4, negative 2, 1/8, and negative 3, boy, it sure looks like those dots are now moving as we move from right to left. It looks like they're getting closer and closer and closer to the y-axis. But it doesn't look like we're ever going to hit those. We can't, because on the y-axis, your x-coordinate is 0, and we made a point of saying that 0 is not in the domain of this function. So what we have now, everybody, is a vertical asymptote right here at the y-axis. And again, it matches the definition a lot of you guys are comfortable with, a line that your curve approaches but doesn't necessarily touch. And so this logarithmic graph is going to look something like that. Okay, everybody, that is where we're at for the graph of f of x equals log base 2 of x. Now, what I'm about to draw, I'm going to undo as soon as I do it, so you might not want to, but just follow along here. If you guys notice, these ordered pairs should all look familiar to you. If we looked at the graph, let me go to green right here, of the basic exponential function 2 to the x that we graphed a while ago, that got us the ordered pairs of 0, 1, 1, 2, 2, 4, negative 1, 1/2, negative 2, 1/4, negative 3, 1/8. That graph had a horizontal asymptote right here at the x-axis, and when we try to draw that, it would kind of look something like this. And what I'm hoping everybody recognizes right here is that in every single ordered pair that we graphed on the graph of 2 to the x, like for example, the ordered pair 2, 4, the inverse of that ordered pair showed up on the graph of log base 2 of x. That was the point 42, and that happened all along. So if we recall what that means then, if these two functions kind of match, but every ordered pair gets inverted, we would say that these two functions are inverses of one another. They should show symmetry with respect to the line y equals x looking like this. And that is exactly what we see. That y equals 2 to the x and y equals log base 2 of x are inverses of each other. Let's explore that idea real quick. If we had y, let me call it f of x, it is a function, is equal to 2 to the x, let's go ahead and let's find the inverse. Switch your x and your y, so we're going to get x is equal to 2 to the y power. And now, if we wanted to solve this equation for y, you guys, this is the reason logarithms were developed and why they were taught to you. They allow you to solve an equation where the variable you're looking for is in the exponent. So what we would probably do right now is simply translate this line right here from an exponent to a logarithm. So this would be log base, and the base of this logarithm is the same as the base of the exponent here, which is 2. So this is log base 2. What comes immediately after the log and the base is the product. The answer to that is going to be x. And then at the end of a logarithm, the answer to a logarithm is the exponent that we used right over here, which is going to be y. So that doesn't really feel like we did anything to solve for y. We just translated from an exponential expression here into a logarithmic expression. And sure enough, we've isolated y. And that is a function. So f inverse of x is equal to log base 2 of x. So, starting with this original exponential function, its inverse ended up being a logarithmic function, notice with the same base each time. Okay, couple quick properties of logarithms. You guys have seen these in the past, and I don't think they're going to give you too much trouble, but let's run through them. The power property is actually the one that we use the most often when we're solving logarithmic equations. It says that if you have a log of a particular base of a product, b, raised to a power, you can bring that power out in front and treat it as a coefficient of the logarithm. N times log base a just of b here. So that's a pretty common property that gets used a lot when we're solving logarithmic equations. So just be aware of that. I got to warn you guys that, and I'm making this up here, but this is going to be a cause of confusion for a lot of you this year. When you go to do an odd homework problem and then you check the book's answer in the back, you might feel like you did everything right, but your answer, you're going to notice, is not going to match their answer in the back. And what you might see then, this maybe isn't the best example, but you might come up with a problem here where your answer would be something like, and I'm just going to make up something ugly here, log base 3 of the square root of 5. And when you go to look in the back of the book, they might have something that looks like this: 1/2 times the log base 3 of 5. And as you look at your answer here on the left, you're going to look then at their answer on the right and think, well, I got this one wrong. Not necessarily. What they did is they treated this square root of 5 here as 5 to the 1/2 power, and then they invoked this power property and brought that exponent of 1/2 out in front. hey, this is big kid math. There's not just one way to do this, and I'm not here to say that either one of these green expressions is better than the other, that one is right and the other is wrong, but it's simply a question of knowing that the same answer can be expressed multiple different ways, and you guys need to be aware of that. So don't panic if that's what they did, but it's not what you did. Okay, moving on here, the sum property of logarithms. If you are trying to add two different logarithms together that have the same base, you can combine those into one single logarithm with the same base, so log base A, by multiplying those two products together. So this is the log base A of the product BC. That's a way you can condense logarithmic expressions as long as they have the same base. Now usually if there's a sum property, I wouldn't bother to write the difference property because people can usually figure that one out. This one, yeah, sort of. Log base A of B minus the log base A of C, again, can be combined into one single logarithm as long as the bases were the same, but now instead of multiplying the B and the C, I think you guys know this already, if addition is going to get you multiplication, then subtraction right here is going to get us division over on this spot, and that's going to be the log base A of B over C. And this last property right here, you guys, is really one that we don't need anymore because we have calculators that'll do this work for us. But the change of base property says the following, that if you're asked to evaluate log base A of B, you can rewrite that as a fraction, and you can change the base of that logarithm to any number you want, and it can be something new. It doesn't have to be A or B. So we're going to change this to a log base C, and it's of the original product, which is B, divided by a logarithm of the same new base as you used on the top, but now, this is weird, the base of the original logarithm now becomes the product of the logarithm down there on the bottom. Now when that would have been useful is if you were asked a weird logarithmic question like, what is the log base 3 of 10? Let's go with that. Let me make it weirder. Let me make that 11. You'll see why in just a second. So the question being asked right now is 3 to what power is equal to 11? There is an answer to that, but it's not a clean answer. We know that 3 squared is 9. We know that 3 cubed is 27. So this answer needs to be somewhere between 2 and 3, and it certainly sounds like it's going to be closer to 2, but we don't have a clue what this thing would look like. Well, in the old days, what we would do then is we would use a new logarithmic base, like for example log base 10, the common log, which we would just leave out, and make it log base 10 of 11 up on the top, divided by log base 10 of 3 down there on the bottom. Or the other log that we use the most besides the common log, which was log base 10, we often use natural log, which I'm hoping you guys recall is log base E. And as long as we use the same log on both the top and the bottom, this should work out either way. So let's try this real quick, guys, and let's see what happens. I'm going to add a calculator page here. I'm going to go Control Divide for a stacked fraction. And we wanted a logarithm right here, so I'm going to hit Control Logarithm. Now I tell you what, on your calculator, pretend it didn't do this, I'm going to just skip the base and just go log of 11, so that means log base 10 of 11. And then down on the bottom, let's do this again, and we're going to go log, and I'm going to skip that and do log of 3. Now when I hit Enter, my CAS gives me the exact answer, but if I wanted it as a decimal, which I do right now, I hit Control Enter, and I got 2.183 for the answer to that. 2.183. That's what I got doing it this way. Let's just prove my point here. It should give us the same answer when we use a different log base like natural log. So what if I did, again, Control Divide, and what if we just did the natural log of 11 over, how about right here, how about we do now the natural log of 3? We're using base E on both sides, Control Enter, and there's the exact same answer again. Now kids, this is how you used to have to do it back in the dark days of the 80s and the 90s and the early aughts. But your calculator now, if you noticed, when I just type in this logarithm, not every calculator out there will do this, but the Inspire CAS will. You can go ahead and put in different bases now. So log base 3 of 11, and your calculator should answer this question directly. Okay, so you can get the same answer in 3 different ways there. All right, like I said, this property, out of all 4 on this page, the change of base property is the least useful to us right now. You absolutely do not need to know that property moving forward. You still can't do it without a calculator, and you guys are going to be allowed to use your newer calculators that are out there. So let's knock this out real quick and then be done for the day, using those properties to simplify logarithmic expressions. So we've got log base 7 of 49 squared. Couple of different ways you could probably handle this, but what I would probably do first, I don't want to sit here and figure out what 49 squared is. It's a big number and we don't have time for that. But we've got a log of a base of a product taken to a power. So we're going to use the power property and bring that 2 out in front and multiply that by the log base 7 of 49. Well, I'm hoping you guys can realize, looking at this pretty quickly, that the log base 7 of 49 is something we can evaluate. 7 to what power is 49? That's 2. So this is a 2 times 2, and we're going to end up with just a 4 for that simplified version in that expression. So that's using the power property. How about problem number 2? We've got 2 different logarithms being added together. We can do that using the sum property, but only because the bases are the same. So putting those 2 together, we can combine this into one single logarithm of the same base, but now in parentheses, we have to multiply the 2 products, which were 30, and then the fraction 5/6. So 30 times 5 over 6. And guys, I'm going to tell you right now, we are not going to be friends this year if you guys are so dependent on your calculator that you don't think you can do a problem like this in your head. The way you multiply a whole number by a fraction is to take the whole number, divide it by the bottom number, and then multiply it by the numerator. 30 divided by 6 is going to get us 5. 5 times that 5 is going to make this 25 here for that product. And log base 25 of 25, think about that for a minute, 25 to what power is equal to 25? That's just going to be a 1. And that's the answer to that second one. And the last one right here, I don't like the way that I typed this, but here you go. 8 to the log base 3 log base 8 rather, of 2. A lot of different ways we could play around with this idea, and I would love to ask people for questions, for suggestions on this one. But what I would probably do here is work on the exponent first. We'll just leave that big 8 the same. And 2 ways you could handle it. I'm going to go ahead and try to evaluate log base 8 of 2. So this is 3 times. All right. And log base 8 of 2 means 8 raised to what power is equal to 2? Well, as I'm hoping you remember, 2 is actually the cube root of 8, which means that 8 to the 1/3 power is equal to 2. So that becomes 3 to the times 1/3, which is 8 to the 1st, and our answer here is just going to be 8. Another way of doing that would have been to reverse the power property and get rid of that 3 and make it an exponent there on the 2. So this now would have become 8 to a power of log base 8, and 2 to the 3rd is 8. Well, log base 8 of 8 is 1, and that ends up just equaling 8 as well. So there's more than one way to skin that cat, ladies and gentlemen, which is an old-timey expression. It's not that Mr. Fontana is just weird and enjoys torturing animals. But anyway, that's all we're going to do here on 1.6. So let's give that homework a try. Let's see how you guys do on that, and let me know if you have any questions. Good luck, everybody.